Section 5.4 is the fundamental theorem of calculus. We did start this in the last section, so this is kind of an extension. Again, the fundamental theorem of calculus: if f is continuous on an interval a, b, then the function that is the integral has a derivative at every point x in a, b, and the derivative of this function is f of x. In other words, if I take the derivative of an integral, I have the function. They undo each other. They're opposite functions, derivatives and integrals. So in other words, the derivative of an integral is the function value. Every continuous function f is the derivative of some other function. Every continuous function has an antiderivative, and the process of integration and differentiation are inverses. So this is a pretty simple way of saying, that says an example applying the fundamental theorem. I don't know why my recording is cutting off the top of my slides. I'll have to see what I can do about that. Example applying the fundamental theorem. So find the derivative of the integral. Again, all we have to do for that, the derivative of the integral is the function evaluated at any value x. It's as easy as that. Now, we also sometimes have to apply the fundamental theorem with the chain rule. So in this case, I do have to use the chain rule here. They go through a u substitution. I will do it that way, but I don't think that you always need to do the u substitution, particularly with a simple function like this. But let's look at it this way. So, looking at my function and taking a u substitution, substituting u in place of x squared. So now again, I just have a simple variable up top. Applying the chain rule, the derivative of the left equals the derivative of the right. The right-hand side is dy du times du dx to get my dy dx. The derivative dy with respect to u times du dx. Again, just writing out what we're taking that first derivative. The derivative of this is sine u times du dx, and then substituting back in place, we get 2x times sine x squared. Now when we were back here, I think that this is a pretty simple function. So taking the derivative, using our fundamental theorem, taking dx of the original integral, we would get sine of x squared, putting this in, and then times the derivative of x squared using our chain rule. Same answer with a lot less notation, but if you like the u substitution, feel free to do that. All right. What happens if our variable is at the lower limit? Variable of lower limits of integration. Wish I could get this to go higher. So that top line says variable example. It says example variable lower limits. Wow. So variable lower limits of integration. So remember in our last chapter, or last section, we learned that we could simply flip the integral. So we're going to simply take the opposite of the integral from 5 to x, treat it like we did previously, and bring the negative sign out front. So we have negative x sine x, dropping this x in. If that had been an x squared, again, we would have used our chain rule. Okay, the fundamental theorem of calculus part 2. This is the one that we use most often. So now instead of taking the derivative of the integral, we are going to evaluate. That's why it's also called the integral evaluation theorem. And again, we looked at this at the end of the last section. The integral from a to b of f of x. If f is the antiderivative, then f of b minus f of a is your evaluation of your integral. Again, fundamental theorem of calculus part 2. Any definite, this is just a continuation of the last screen, any definite integral of any continuous function f can be calculated without taking limits, without calculating Riemann sums, and often without too much effort, so long as the antiderivative can be found. So let's do an example of this. So the first thing I want you to think about is, can we find the antiderivative of this? So find the antiderivative. So the antiderivative is x cubed plus 3. We are going to evaluate this from -1 to 3. If you remember, that means we evaluated at 3, plugging in, minus evaluating it at -1, and we get 32 for our answer. Okay, so pretty simple to find an antiderivative or to find an integral as long as you know the antiderivative. We're also going to use this to find total area analytically. Remember, total area could span above or below a region or an axis. So to find the area between the graph of y equals f of x and the x-axis over the interval analytically. So first we have to find where are the zeros of f, integrate f over the subintervals split up by the zeros, and add the absolute values. Remember, total area is the absolute value of the integral. So, whoops, I thought I had put in a slide to do this. Well, let's see, maybe I did add it at the end. So again, finding the area between the graph of y equals f of x can also be done with your calculator. I guess I didn't put the example in, but let's do this. We want to find the area. This is the total area, so absolute values involved, of y equals 4 minus x squared from 0 to 3, and the x-axis. So the area between this curve and the x-axis between 0 and 3. So first let's just take a look at this function. 4 minus x squared, that's an upside down parabola, passes through 4, has zeros at 2 and -2, and looks like this. So if I want the area from 0 to 3, that means I'm doing this area here and this piece down there. So I have to break this into two regions so that I can integrate over that 0. So I'm going to take the integral from 0 to 2 of 4 minus x squared dx plus the absolute value, and these have to both be absolute value, of the integral from 2 to 3 of 4 minus x squared dx. We often also say, I know that this is positive because it's above the axis. So if I subtract the second half of this, since that would have been a negative part of the integral, I will get a positive and a positive. So either way will work. Again, our antiderivative here is going to be 4x minus 1/3 x cubed. I'm going to evaluate that from 0 to 2, and then I'm going to subtract again my antiderivative evaluated from 2 to 3. Remember, the reason I'm subtracting is because this second piece is underneath the x-axis or negative, so to add it in to find absolute area rather than the displacement, distance versus displacement, remember, then I'm going to use a minus sign here. So again, evaluating this, if I plug in 2 here, I will get 16/3 from 2 to 0 minus 7/3, well, excuse me, minus a -7/3, which will give us 23/3. Okay? And you can do that math on your own to see if you can get the answer. And then I would also like you to try this using your function on your calculator, plugging it in to get NI and T. Okay, so take a look at those. We'll do a few more in class, but that's it for the lesson.